Okay, let's go ahead and start the class. Let's see what we have here. Today we are going to talk about the exam a little bit. Next week we'll have the first exam, which will cover chapters 1 through 3. And which will cover chapters 1 through 3. And we will finish the source panel example we were solving. And we will move on to solving some example problems. Essentially, we are going to solve problems from the previous year's exam 1, right? Yeah, let's talk about the exam first. Your exam is going to be 1 hour and 15 minutes. It will be held in class. For the online students, you should join the class online, of course, on Blackboard. I will post the exam on Blackboard. You should take the exam at the same time as the other students if you're an online student. If you can't make this, so we have a student, for example, who is in China and definitely can't make it to the class in time to take the exam. So if you have this type of situation, I can definitely work with you and give you the exam outside of the regular exam time. So that's for the exam time. And if I'm going to ask my grader to come in and proctor the exam for us, if you needed more time after 1 hour and 15 minutes, and if there is no class here, I don't have any objection of giving you more time, right? So you can have as much time as you need for the exam. Of course, not as much as you need. Yes. We'll talk about that. We'll get there. Okay. Is there any question about the exam time? Not another time. Okay. So about the question, as I said, we will cover chapters 1 through 3. And then on the second exam, we will do chapter 4, 5, 6. And some flight mechanics that we will cover. We'll do some flight mechanics as well. And on your final exam, we will have all of the material that we covered throughout the semester. Okay. So how many, let me write it on the board just to make sure. Exam will be exam 1. It is March 10th, right? And 5:30 p.m. So next Monday, next Wednesday, in a week, in 7 days. And there are a couple of people who have talked to me and cannot make it to this time for the exam. I will go through your problem. We will definitely try to help you to take care of you and find a way for you to take the exam outside of this time. But if you don't have any legitimate reason, you have to come to class, okay? And unless you're an online student. But the number of questions, we will have 10 questions that are descriptive or multiple choice. Or multiple choice. Okay, what does a descriptive question mean? For example, like I'm going to read a question from the previous year. And that's the first question on the previous year's exam. Explain how one can investigate whether a flow is kinematically possible in compressible flow field, right? The clue here is that the flow should be kinematically possible. So conservation of mass has to be true. And the next clue is that it is an incompressible flow field. So for an incompressible flow field, the continuity equation was simply this. So to answer that question, if you just write del dot V is 0, should be 0, or you just explain it. the time rate of change of velocity has to be 0. That's it, right? It shouldn't take you more than like 10 seconds to answer this question if you know what you're talking about. Okay, that was the first question. I mean, surprisingly, a lot of people, as far as I remember, couldn't answer this question. And from your faces, I'm guessing that you couldn't answer the question either, which is most of your faces. But yeah, you can definitely. I forgot to talk about this before. You can definitely bring since you have an online section and there is no way for me to control the online people, exam will be open book, right? So you can use the book. You can also bring in the homework solutions. Again, it is because I don't have any control over the online people. So whatever they can use, yes. Notes, yeah, lecture notes, open everything. Let me change it. Open everything. All right. Lecture notes, homework solutions, online material, whatever you can print and bring to the class, and the book, of course. But to be honest with you, if you need more than an equation sheet, this essentially means that you haven't studied enough. Okay, because going over the book to find the answer to a problem is just going to take your time, and you probably won't be able to find an answer. That has been always my experience when I was a student. So when I needed the book, it meant that I didn't study enough. Okay, but you can bring everything to the class, whatever you need, whatever you want to use. Okay, you can bring your laptop, you can Google things, right? And the main reason is I don't have any control over online students, right? So whatever you want to bring, you can bring to the class. Yeah. So this essentially means that I cannot give you any problems out of homeworks, like straight out of homeworks. Right? All of the problems have to be fresh. They will be similar to homeworks or the problems we have solved in class, but they won't be the exact problems, right? Which is something I did in the previous years. I usually gave one problem that was the exact copy of the homeworks or the problems I solved in class. Okay, so open everything, right? And yeah, there will be 10 descriptive questions and or multiple choice. I will make sure that you won't need more than 10, 12 minutes to answer these questions, right? So easy questions and very small answers. Just write this down. You get the answer. Any questions about the descriptive part of the exam? Let me read you another question. Let's see if we can answer this. Okay. I don't know what is going on with my laptop. I'm sorry about the sound that makes. So, and let's do this today. This is what I usually do for the exam reviews. I give you the question. If you can answer it, you'll get a bonus point, right? What is the center of pressure? That was another question. Yes. Where all the moments are, the combination of all the moments that are created by the forces is going to be 0, right? So sigma m is going to be 0, exactly. Let me write your name down. Jacob, right? Okay. So see, very easy to answer as long as you know what the center of pressure is. So, and then we are going to get 4. I'm debating this. I haven't designed this part of the exam yet. So it really depends on how hard the questions are. But 4 or 3 problems that you have to solve, depending on how hard the questions are, right? I'm designing the exam for a 75-minute exam. So we should be able to answer all of the problems. And the problems are going to get harder as you progress through the exam. So your hardest question will be the last one, right? And this is for undergrads. So people who have taken the 578, EMCH 578. But if you're a graduate student, you will get 4 to 5 problems. So essentially for graduate students, exam will be exactly the same, except for one additional question. And that additional question is usually a creative type of question. So the solution shouldn't take you that long, but you have to be able to be creative. Yeah, you have to be able to come up with a creative way to solve a problem, right? So it is I can say it is a harder problem to solve, right, compared to other questions. Yes. Uh, you know what? I usually don't do that mainly because I don't want undergrads to be obsessed with solving a bonus point and losing the point on the other problems, right? But let's do this. If you have solved all the other problems, and if you solve this fifth problem or fourth problem, then you'll get a bonus point. But if you just solve the bonus point and like leave other problems empty, don't solve them, you won't get any points, right? Because I want undergrads to focus on the other problems, not this one. Does this make sense? Okay, so I guess, yeah, let's do this. Is there any other questions about the like exam procedure? So make sure you study the material. If you can watch the lectures, go back and watch them. Let me put it this way. I usually focus on something that I'm interested in, right? So if I see I'm focusing on something, I keep talking about it. This essentially means that I have it on my mind and I want to give it to you as an exam problem, right? I guess that does make sense. So yeah, and I guess that's it. Is there any questions? How do you feel about the exam? Are you worried, or do you think it's going to be harder compared to other courses, easier, same difficulty? So same difficulty. You're not that worried. What does so mean here? Okay, more worried than. Why is that? Okay. 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 Not really. No. If you can solve all of the homework problems on your own, right? If you are solve the example problems we have solved, then you shouldn't have any difficulty answering the example. That is my idea. Of course, some students usually disagree with me when they see the exam, but that's the dynamic that always happens, right? I don't want to like. There is no point in failing you guys, right? For me, right? I don't get any extra like bonus, right? So but the goal here is to teach you aerodynamics and to help you get a good grade out of it, right? So don't worry about the exam if you're worried. And I understand the material is a little harder than your previous like fluid related courses due to the multitude of reasons, but hopefully we have talked about the material enough. So if there is no question about the exam, we can go back to the example we were solving in the previous lecture from the source panel theory, and then we'll move on to solving the exam problems from last year. So source panel theory. And there, as you know, there is also problem in your homework from source panel theory, but I don't see how this should be part of your exam. Right? So what we did was we came up with the final solution to we wanted to find this. Do we all remember the previous lecture's material, right? Or do I need to like give you a summary? Give a summary, okay. So the idea was we are going to, let's actually start by solving the example from the beginning. The idea was we wanted to use this source panel theory to solve the non-lifting flow around a circle. That was the main idea, right? That's what we wanted to do. And the main idea of the source panel theory was that we can divide your geometry, whatever that is, to different panels, like straight panels. And these panels have a source strength, lambda of j. But in this case, in this problem, we have divided the cylinder to 8 panels. And eventually, we are going to find the velocity of each panel, v of I. Right? The velocity of the control point on each panel. Right? And this velocity is going to be, we are going to assume that this velocity on the panel is not going to change. So if you have the velocity 2 meters per second here, your velocity is going to be 2 meters per second here, 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 here. And it's only going to change when you move on to the next panel, okay? And when you find this velocity, we can use the equation for Cp. And we can find the pressure coefficient on each panel. When we have the pressure coefficient on each panel, we essentially have an estimation of the pressure distribution over the cylinder, okay? But the main equation we had to solve to find this lambdas, the strength of the sources, was this one. Lambda I divided by 2, lambda of a panel divided by 2, sigma of, and then we went to over all the other panels that are inducing some velocity on the panel of interest. So lambda j over 2 pi integral of over that panel, partial n, natural log of Rij, dsj plus v infinity cosine of beta I. And cosine of beta I here, or beta, is the angle, your normal vector to the panel makes with the flow direction. Okay, that was the idea. This will give you this specific one for one panel will give you one equation, and for this specific problem, 8 unknowns, 8 lambdas, right? And then let's say we start with this panel. If you write the same equation for this panel, you're going to get another equation with the same 8 unknowns until you get 8 equations. I'm sorry, with 8 unknowns, right? And then you can find this sources, okay? And the idea is we are in the non-lifting flow, in compressive flow. Vn in the normal to the panel direction is 0. That's why we have this equation. So we only have V tangential to this panel. And that's where the other equation we have to solve comes in. Your V of each panel, which is going to be equals to Vs, V tangential to the panel, plus V infinity sine of beta I is going to be equal to lambda I, V infinity sine of beta I plus sigma j to n, the number of panels, lambda j divided by 2 pi integral of partial s of natural log of rj and dsj. Using this equation, we could have, if you find all the lambdas, you could just plug that in and get the velocity for each panel. Of course, you don't need to do all of these with your hand. As long as you have the correct setup, you should be able to just plug that in an Excel or a MATLAB code, and it will spit out the results for you. Okay. Is there any questions here? Okay, so the goal here, the first part of the goal here, is to find in the example that we are really interested in, and this is called, for simplification, we are going to call it I of I and j. The first thing you want to do when it comes to this type of problems is to calculate I of I and j. If you recall from the previous lecture, we stopped here. We calculated the partial and I of natural log of r ij, okay, which was equals to xi minus xj cosine of beta I plus yi minus yj sine of beta I. Just to make sure we are on the same page, I think I need to mention. So I here represents the panel you are working on, and J represents all the other panels that are going to induce a velocity on this specific panel, okay? So I can be 1. When that's the case, your J is going to be this panel, this panel, this panel, this panel, this panel, this panel. So all of these, and then you do a summation to essentially sum all the effects of the other panels on this one panel. And this natural log was divided by xi minus xj squared plus yi minus yj squared. Okay. So we have the derivative of the natural log. You just have to plug that in the integral and do the integration. We actually, what we were doing was we were assuming there are these two panels. This one is panel I, and this one is panel J. These are arbitrary panels. So we are finding a general solution, essentially, that we can just simplify to fit that problem. And you're going to see why that is going to be helpful to us. Control point xi and yi. Then this point is xi and ii, xi plus 1, yi plus 1. These are capital X's. This one xj, yj, xj plus 1, and yj plus 1, xj and yj. The flow direction is this. Normal to the flow direction, this will be giving you your beta I. Here, the flow direction is this. Normal to the flow direction is this. What is our beta here? Which of these angles is going to give us the beta? Exactly. This one is going to be beta j, right? Again, we are trying to find a general solution. So if you find this general solution, you can essentially use that general solution and apply to any source panel problem that you want to solve. You don't need to go through all of these integrations and these things yourself. Okay. Your book has done some simplification in solving this example problem to make everything a little simpler. I'm not going to go over this. I'm just going to give you the solution to the integral, right? And the solution to this integral, I'm talking about this integral. So essentially, I'm going to give you the I of I and J, right? If you're interested to understand how your book has done this, you can, of course, go back and look. And this is for an arbitrary shape and arbitrary panels, right? An unlimited number of panels. So we can apply this problem to any shape. It doesn't have to be this 8-panel system. This will be your integral. I'm going to tell you what all of these constants are. C over 2 natural log of Sj squared plus 2a Sj plus b divided by b. I'm going to tell you what all of these are. B, a, d minus ac divided by e, inverse tangent of Sj plus a divided by e minus inverse tangent of a divided by e. Okay. S of j is going to be this length, the length of your panel, the length of the jth panel. This is S of j. A is, all of these are represented by constants. So I'm just going to write them down here. Or I can actually just xi minus xj cosine of phi j. It's going to take us a long time, but that's all right. And phi I here is this angle. Phi j is going to be this angle. It's going to make it's going to be simpler when you apply it to a specific geometry. Let me just write all of this on the board for you. Xi minus xj squared plus yi minus yj squared. This is for B. And then for C, you're going to get sine of phi I minus phi j. We give you D and the rest of them here. D is going to be equal to yi minus y j cosine of phi I minus xi minus y xj. I'm sorry, so these are lengthy equations. You just have to bear with me. So I give them all of you, or I could have just posted them on Blackboard. But and Sj, as I said, is the length of the jth panel. So a square root of xj plus 1 minus xj squared plus yj plus 1 minus yj squared. And E is the square root of B minus A squared. Okay, so let's see how would these look when you are looking at this problem. at this specific problem. Let's do the problem in your homework. The same circle, only 4 panels. The direction of these panels you can choose. You don't have to follow the direction that I'm drawing here, but let's do this. Let's say this is panel 1, panel 2, panel 3, panel 4. Okay. For the time being, for the first one, let's say your panel 1 is your ith panel, and your panel 2 is your jth panel. So we want to find how much velocity this panel 2 induces on 1, right? So come back here, look at this plot, which is also in your book. You have xj plus 1, y I plus 1, and let's say this is actually with a radius 1, right? What would be the points we're going to get here? The end starting points for panel 2. The radius is 1, right? So x squared plus y squared is going to be equal to 1, right? Okay. And the angle here, this is something that I set, and I'm going to set the angle here to be 45 degrees, which is sine and cosine of 45. What is sine of 45 degrees? Or pi over 4? Does anybody remember? Okay. Can you say it in a square root of 2? That's it. Okay. So your x value here is a negative sign. Your x value is going to be negative the square root of 2 divided by 2. Your y value is going to be the square root of 2 divided by 2, positive, right? That's your xj, and yj, right? In all of these equations, xj and yj will be those values. And then xj plus 1, yj plus 1 here is going to be positive, the same values. That's why having only 4 panels is going to make it easier, right? The square root of 2 divided by 2, the square root of 2 divided by 2 for x and y, right? And then your beta, the flow direction is this direction. Your beta for this third panel is going to be equals to 90 degrees, right? I'm sorry. They are in the same direction. So 0 degrees. But for this panel, they are in the opposite direction. So your beta is going to be 180 degrees, right? For this panel, you're going to get your flow is in this direction. Your beta is 90 degrees. Okay. So we have all of the betas, right? We have all, whenever you have sine of beta or cosine of beta, you can plug those values in. For your phi, we define phi of I as pi over 2 plus beta, or we define beta of I as phi I plus pi over 2, right? So when your beta of I is 0, your phi of I is going to be negative pi over 2, right? Does this make sense? That's just by the definition, right? This is pi beta of I. If you add it by pi over 2, you're going to get phi of I. Okay? And this is the angle there. And for phi of j, it is beta j minus pi over 2, right? So you have a positive sign, you have a negative sign over there. What is your beta j in this specific problem? Is 180 degrees, so you can find phi of j, right? You see all of these values that are in all of these long equations, you can just find the values for them and plug them in. So eventually you're going to have your A, B, C, and D, and you will be able to find I of I and J, right? Just have to make sure you have the correct points, correct angles. Just plug in into these values. Should be able to get I of I and J. When you have the I of I and J, you can go back to the equation of Vn, right? You remember that equation, V infinity cosine of theta plus lambda I divided by 2 sigma of whatever, right? Plug the I in there, you're going to have the equations you need to solve the problem. One equation. Then you do it for the next panel, you're going to have another set of equations. You do it for the next panel, another set of equations, so on and so forth. Is this clear? So, yes. This one. What is equal to 0? All of the panels. That's the idea. All of the panels. That was the idea, right? You're going to actually, at this point, you're going to get a stagnation point. That's the, so Vn is 0 and Vs at the center of it. Okay. I'm not sure. Do you have any questions? Or is it just very confusing? That's why you don't have any questions. Yes. It wasn't about betas and phis, no. It was just about the points, right? That's how I chose my points, right? You could have chosen it this way, right? Right? Like 5 panels, right? But that, since finding those points would have been much more difficult, right? You're doing yourself a disservice, right? Especially if you're doing it by hand. 0, yes, definitely. Yeah. You can do whatever you want to do. You can you won't get this problem on the exam. There are two reasons for it. It looks very confusing. I understand that, right? But when you have all the points figured out, the only thing you really need to do is to plug the values in these, like find the final values. So it's just a summation, a matter of summation, right? So do the summations, get I of I and J. Then you do, like, let's say, if your I is 1, you find I of 1 and 2, I of 1 and 3, I of 1 and 4, right? That's it. And then you go back to the equation, plug that in. It will give you a lambda 1 divided by 2, lambda 2 multiplied by a value, which is I of I and J, right? Lambda 2, lambda 4, right? That will be one equation. Then you get you do the same thing for panel 2. I of 2 and 1, I of 2 and 3, I of 2 and 4, right? Another equation. I of 3 and 1, I of 3 and 2, I of 3 and 4, another equation, right? So solving the problem is not that hard. It just can get confusing because there are a lot of numbers involved, but there's no specific, like, concept to it. I mean, you don't have to solve a partial differential equation or like take the sine or cosine or whatever. Okay, so are we clear on what to do for the homework problem? For the homework problem, you define your panels. Let me actually try doing this, just to make sure you are a little more clear. And you have the answers for the 8. You have to compare your final homework problem solutions, pressure coefficients, to the pressure coefficient of the example in the book, right? This is a book example, the 8-panel one. You can just go back to it and get the answers from the book. If you don't have the book, I can give you the solutions to that. But let's do this. Let's actually do what Joshua want to do. Okay, you wanted to do something like this, right? Okay. Let's say this is panel 1, panel 2, panel 3, panel 4. Okay. And what is X and Y here? If it's a, like, if your radius is 1, X and Y is going to be -1 and 0, right? What is X and Y here? 0 and 1. What is X and Y here? 1 and 0. What is X and Y here? 0 and -1. We also have to have the point for the control points. So a small x's, right? These small x's are the control points. So in the middle of the panel. In the middle of this panel, we have to find this value. What is the value of X here? How can we find that? Cosine of what? Okay, so cosine of 45, this is 45 degrees, right? I think they are angry. Cosine of 45 is going to be equals to what? Cosine of this theta. But no one remembers. So it will give you the length of this line, but it won't give you the projection here. I guess we can do this. You have to do some calculations, right? But eventually, what I assume you're going to get, that's why I did the other paneling scheme. That would have been easier when it comes to the middle panel. But you are connecting to the middle of this line. Let me leave it to you. So you have to find, let's say X, these are all 1/2, right? 1/2 and 1/2. Then 1/2 and -1/2. -1/2 and -1/2. Here we have 1/2, -1/2, and 1/2, right? So we have all the control points. We have the starting and ending points. And the next thing you want to find is the angles, beta and phi, okay? What is the beta for this panel? This is the flow direction, right? This is the normal direction. What is this angle? It's going to be pi minus pi over 4, right? Pi minus 45 degrees, or pi over 2 plus 45 degrees, right? So 3 pi over 4. That's the beta for this angle. What is the beta for this one? Only pi over 4. The beta for this one is -pi over 4. And beta for this one is -3 pi over 4. We have all the betas. And then we need to find the phi for all of them. The idea was beta I is pi over 2 plus phi of I, right? So if you have the beta I, pi over 4 here, then your phi R is going to be, for this one, -pi over 4, right? For this one, is going to be 3 pi over 4 equals to pi over 2 equals positive pi over 4, right? And so on and so forth. So you find all of these angles and all of those things. The next step would be to find the i's, right? Let's take this panel 1 as the ith panel. So I is equals to 1. And then your j has to go from 1 to 2 to 4, right? So we have to do 2 first, then 3, then 4. I of 1, 1, and 2. What was that line formula we had for I? It was C over 2 natural log of Sj, 2a Sj plus b plus b. So Sj here is going to be the length of your jth panel, which is 2 in this case, right? What is the length of this panel? Pretty easy to calculate, right? This, you have 1 here, you have 1 here. Square root of 1 plus 1, right? Square root of 2. That will be the length of this panel. So Your S, you have your Sj. But let's do, for example, A. A, it says negative xi, the small xi minus xj, right? Your xj is this one, right? That's the capital Xj, right? But your xi, that's the x small xi in the formula for A, is this one, right? So you can always, if you were confused about i's and j's, you can always come back to this picture to give you a clue. So you plug the values in, you have all the values, you plug those in. We have, so xi here, the small xi is negative 1/2. Xj, which is the starting point of your j's pattern, that's the capital Xj, is 0, right? So negative 1/2 minus 0, negative 1/2, right? Then you have cosine of phi of j. Phi of j is negative pi over 2, pi over 4. Cosine of that, you can calculate it. Then you go through all of these steps as it is laid out here. You will be able to find A, B, and C, and D, and all of those things that you need to find. Right? Does this make sense? It's just, you just find the points, plug the values in. That's it. You should be able to find a number. Okay? Does this make sense at all? We have two people who understand this. Let's go one by one. Do you understand this? Okay, you understand this part. But you understand? Okay. Okay. Right. What about you? Okay, that's good enough. You don't understand it? No. Go back to the equations. Right? I gave you all the equations. Like you see in all of those equations, we have capital Xj, capital Yj, Yi, Xi, Xj, right? We have all of those values. So you just plug these numbers in there. Get the values. I don't know if that answered your question. So we have a set of equations. You just have to find the points for them, plug the numbers in inside those equations. That's correct. Each panel, yeah. A starting and ending point of each panel matters, yes. No. The value you're gonna find for velocity is the value of the velocity at the middle point, right? It's the same thing for computational analysis, like fluid. You find the value for the center of the cell, and you assume that value applies to all of the cell. We are going to find a value for a velocity at the control point, but we are going to assume that the velocity is going to stay the same throughout this panel. But to find that value, we're going to need the starting point and the ending point, right? Does it make sense? Okay, so next person who is avoiding me. Can you call him? No. The one. Hey. Do you have any questions? No. So you understand it, or you're very confused? Which one is it? At the middle. Somewhat confused. Some. Okay. And you don't know where's the question. You don't know what is it. You can always come to my office and we can talk about it. Okay. 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 That's good. That's very good. That's the idea. It's not. It is one of the homeworks. Not on this exam, at least. Do you know where the confusion is? Can you ask a question? I didn't understand the question. That's all right. Just no worries. If you don't know where I understand it can be very confusing because we are dealing with a lot of equations, a lot of numbers, right? And the idea is you eventually have to plug this into a like MATLAB code, right? That's why it gets a little confusing. Sure.
How do you know which point is like the I plus one, just the I? Like for capital XI versus capital XI plus one.
That's when you start moving, right? We start moving from here to here, right? That's what you define. You can move it in the other way.
Okay, so like for if you're doing panel one on panel two, do they both have to go like this way and then this way?
You have to be consistent.
Okay.
Yep. That's the idea.
So we don't ever really use the I plus one though in any of the equations.
If you don't have it, no. But the thing is, I plus one will be the j plus one in another like panel, right? So you have to find the number. So I don't know her name. So that's it for you. Do you have any questions? Shelby, right? Yeah, I had to think about it. Sorry. Okay, so let's go to Trevor. That's correct. Yeah. We'll get there. So as long as you understand up until this point, you're fine. Okay. 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 Yeah, that makes sense. That's correct. That's correct. Big X and big Y identify the starting point and the ending point of the panel. A small X and Y identifies the control point, the middle point of the panel. Okay, it can be XI, XJ, X whatever, right? As long as it is a small, it's the middle point of the panel. But if it's like big, capital, then a start or ending point of the panel. Okay. You're good. Okay. What about you, Joshua? Do you have any questions? You're good. Okay. So hopefully we understand how to get to this point. But then if you calculate all of these i's, I1 and 2, I1 and 3, I1 and 4, I1 2 and 1, all of those, like as many as i's you have, you come to the equation we have for the velocity, or the equation we got from the normal velocity, right? We have this general main equation, gamma I divided by 2 plus sigma of j equals to 1 to n, where ij cannot be equal to I, and then lambda, not gamma, lambda j divided by 2 pi I of I and j equals to, no, plus the infinity cosine of beta I. Okay, so let's say we have already calculated all for panel 1 are all of I and j's. Like I1 and 2 is, let's say, 0.3, 1 and 3 is 0.5, 1 and 4 is 7, right? Random values. I don't know what they're going to be, just most random values you can get. Okay. And this I is panel 1. I is 1. We are on the, so your equation is going to be lambda 1 divided by 2 plus Then we're going to do the series, right? Lambda 2, which is your j, right? J cannot be equal to I. So we're going to start from 2. Here, lambda 2 divided by 2 pi multiplied by I of 1 and 2. So lambda 2 multiplied by 0.3 divided by 2 pi. Yes. We are solving for all lambdas. Just wait. Just give me, just wait a minute. Okay. So the first term of this series is going to be 0.3 lambda 2 divided by 2 pi, right? The second term of this series is going to be lambda 3 divided by 2 pi I of 1 and 3. I of 1 and 3 is 0.5. Yeah. So this is the second term of this series, plus the last one, I of 1 and 4, 7 multiplied by lambda 4 divided by 2 pi plus V infinity cosine of beta 1. We said beta 1 is this, right? So pi over 4 plus 90. Cosine of pi over 4 plus 90 is the value you have, right? You can calculate that. Plus pi over 2. Okay, so that's it. This has to be equal to 0. This is your first equation and 4 unknown lambdas. Okay. Then you move on to I equals to 2 as your second panel, right? For that second panel, when I is equals to 2, you have to find I, 2, and 1, I, 2, and 3, I, 2, and 4, right? Then you'll get another equation. The second equation will be lambda 2 divided by 2 plus I, 2, and 1, lambda 1 divided by 2 pi, and so far and so forth, right? Does this make sense? Yes? So you're going to have 4 equations and 4 unknown lambdas. You should be able to find all of the lambdas. Okay? When you have all of the lambdas, I want to solve some examples for the review, the exam, but I guess we don't have any time. But when you have all of them, so is this clear now? Is this clear what you want to do? As soon as you find the i's, you come to this equation, plug all of your values in, you're going to get, for this 4-panel system, you're going to get 4 equations and 4 unknowns, right? Which you can solve. I guess you don't want to solve it by hand. Yes. V infinity is constant, is given, right? You can do whatever you want to do with it. You can, yeah. And eventually, it doesn't really matter what is the value of V infinity, because your pressure coefficient equation is 1 minus VI divided by V infinity squared, right? So V infinity should cancel out eventually at the end when you're dealing with the pressure coefficient. Is there any questions? No? Okay. So we understand how to get here, right? You have all of the A's and B's and C's as all of those things. Calculate the I's for each panel, right? Then you write this one equation. Then you move to I2, write the second, third, fourth equation. Okay. And you have, based on this system, the system of 4 equations and 4 unknowns, you will be able to find lambda 1, lambda 2, lambda 3. What is the lambda 1, lambda 2, and lambda 3? Is essentially lambda 1, lambda 2, and lambda 3 are the strength of the sources you need to maintain flow, cylindrical non-lifting cylindrical flow, non-lifting flow over a cylinder, right? Those are the source strength you need. She was first. Go ahead. You had a question, right?
Sorry, here we have 4 lambda, and for each lambda, we are required to find 3 I.
That's correct, for a 4-panel system.
We have 4 multiplied by 3, which is 12 I.
Okay.
It doesn't seem logical to do it by hand.
No, it doesn't. It is a computational method.
So how we should do it for homework?
You can just write the equation and do it through using MATLAB or Excel. Okay. Yeah, it is a, keep that in mind. It is a computational method, right? We want to, instead of having an analytical solution, we want to have a way to write a code for it. Okay. You don't need to use MATLAB code as long as you understand how to use Excel. You should be able to do this as well. Yes. Okay, so the whole idea came from the potential flow theory, right? In potential flow theory, we combine two simpler flows, what we call elementary flows, right, together to find a more complex flow, right? That was the idea. Here, we are going to combine these panels, these source panels, right? These are source flow panels, right? With the incoming uniform flow to mimic flow over a cylinder, right? Non-lifting flow over a stationary cylinder. That's the strength of the source you need to have that type of flow, right? So if the strength of the source, if you change the strength of the source, you essentially are not going to get a flow that is similar to flow past the cylinder. Okay? So, and then let's say we have all the lambdas calculated. Then the next step is to find the velocity, right? How do you find the velocity? Your velocity of each panel is going to be equal to V infinity and S plus sigma of J equals to 1 to N, V infinity and S sine of beta. The sine of beta I, right? Plus lambda J divided by 2 pi integral of partial S natural log of Rij ds. Okay, so you thought up until this point it was a lot of work and a lot of calculations, but you essentially have to do the exact same thing to find VI, right? This is the exact same formula. The difference is we have to calculate a new partial. That one was partial n natural log of R. This one is partial S natural log of R. But the good news is we have calculated the integral for you, and I'm going to just give you the values you are going to need. So this integral is going to be equal to D, and D and A and C are the previous values of D minus AC divided by 2E natural log of SJ squared plus 2ASJ plus B divided by B minus C inverse tangent of SJ plus A divided by E minus inverse tangent of A divided by E. Okay, and this will give you your velocity of each panel. You know, this will give you the value for that integral, right? And then you just have to plug it in, plug this whole thing into this equation. The infinity sine of beta I plus sigma lambda J 2 pi multiplied by this. But again, you're going to have 12 values for this integral, right? So it's going to be the same thing. But since you already should have all of these values, just plug in the numbers and do the calculation. Okay. This part clear? So we found the lambdas, we found the strength of the sources. We have another equation, this one. But here for this equation, we already have all the lambdas, right? Let's say, let's call this integral. This integral is not called I. Let's just call it the capital J of I and J, right? Essentially, your V of panel I, if you do this calculation, your V of panel I is going to be equal to panel, let's say panel 1, is going to be equal to V infinity sine of beta 1 plus lambda. This time actually J can be equal to 1. So lambda 1 divided by 2 pi multiplied by the solution to that integral, J of 1 and 1, whatever that value is. And lambda 2 divided by 2 pi, J of 1 and 2, plus lambda 3 divided by 2 pi, J of 1 and 3, plus lambda 4 divided by 2 pi, 1 and 4. Okay, so you already calculated of J, the J value. This is the J value, right? That integral that I'm going to call J, right? You already have calculated all of the lambdas. You should be able to have velocity of each panel. And then you do the pressure coefficient. You find the pressure coefficient on each panel, which is equals to Cp equals to Vi minus V infinity divided squared, right? 1 minus Vi divided by V infinity squared.
Can you include its own, like, for that one, if you want to included lambda 1 in it?
Yeah, we don't have the obstacle we had over there. But eventually, it shouldn't really matter. But you'll get it when you do the solution, right? Okay, so okay. Let me ask you this, and what you need to do in your homework, finally, as a final part of the solution, and you should keep in mind that the last 2 questions on the homework I will grade myself. My grader, because my grader doesn't know these, and I will grade them myself. What eventually you need to present is Cp versus theta. Okay, if you recall from our analysis, analytical analysis, this was the analytical solution. 1 here, and the most negative was -3, right? If you have 8 panels, you're essentially going to have 8 points for Cp, right? And based on what your book has done, you're going to get this point, you're going to get this point somewhere here, and this will be your, how many points do you have? 1, 2, 3, yeah, 8 points. You're going to get 8 values for the pressure coefficient. How many values are we going to get if you have 4 panels? Only 4. And their location on this plot really depends on how you choose the configuration of your panels, right? If you go with the original configuration I proposed, we are finding the pressure coefficient at these locations, right? This is your theta 0. So we are finding the pressure coefficient at theta 0. This is Cp versus. This is theta 90 degrees, right? So we are finding the pressure coefficient at theta 90, wherever that is. And then only 4. You have to compare your results and see what kind of a line you're going to get, what kind of a distribution of pressure coefficient you're going to get with the 8 panel result. Okay. Is there anyone in this class? And it's all right if you don't know this. You have a question? No. I was talking to you, but that's all right. No. Is there anyone in this class who doesn't know how to implement something like this in MATLAB? Or yes, there's 1, 2, 3, 4, 5, 6, 7. Okay, a lot of people. I guess you have to solve it by hand then. Yeah, and
If you're going to do it in MATLAB, we need to solve a lot of equations by hand.
You-
So even if we are using MATLAB, we have to solve a lot of those equations to know the unknowns and plot the values in MATLAB.
why would you want to?
Efficient here. We don't have all of the
No. As long as you have these points, as long as you give the correct points and give the correct equations, you don't need to do any manual labor.
For each line, we have 3 points.
Yes.
And
So you
then
just have to have 20, 30 points. That's it. Inputs, yes.
We do have to solve for A, B, C, D, E, right?
But those are really just a separate set of equations, right, in MATLAB.
C is like 1 line, right?
Yeah, so what I'm going to do is your homework due date is on Monday, right? And I don't think I can get to post anything before Monday for you guys. What about the final difference part of the homework? Have you looked at the homework at all? No. We have 1, 2 no's, like very straight no's. We have 1 yes. No. Who has looked at the homework other than 2 people? So 4, 5. Okay. How did you feel about the final difference part of the homework? Was it understandable, workable, or no? We essentially did it in the class. So if you were in the class or you watched it while I posted. So let's do this. What I'm going to do, since we don't have the online students, I guess their opinion. If you have an opinion, online people, please write a comment about this in YouTube or Blackboard. Any of them, doesn't really matter. Let's do YouTube. And what I'm going to do, if you don't need the solution to the homework, right, I can extend the homework to Wednesday, right? And then I can post something for you that is going to help with implementing this in MATLAB, which is going to be pretty easy on it, to be honest, as long as you define the correct parameters and you define the correct, I guess solving the four unknown for equations maybe a little hard. Do we know what is Runge-Kutta method? Yeah, Runge-Kutta or Runge-Kutta. Yes. Okay, that's all right. I can post something on Monday if you don't mind not having the solution to homework 3 by your exam time. Yes. I've been a student myself, so postponing the exam is not gonna help you study more. But most of the problems of the homework will be on the exam, right? Yeah, that's and I'm already postponing it to Wednesday. So, no. What do you think about that? What do you think about postponing the homework due date to Wednesday instead of Monday? Is that going to help? And then I will post something on YouTube to help you with the MATLAB implementation. Yes.
it would be better to do the last question of the homework, this one. I mean, to extend the due date of that question.
No, I'm not gonna do that. It's going to be the whole homework because that's going to be a mess for me and my grader to solve to grade the first 4 problems. Yeah. We will solve some example problems for you on Monday. That's what I was planning to do anyways today. Yes.
So what you're saying is if we practice do on Monday, and you'll release the solutions on Monday so that we can use those to study.
That's the idea. Yeah.
We'll be able to get the lecture.
Can you repeat? I didn't hear you completely.
So like, why are you postponing the homework until Wednesday?
Because so let me ask you, and let's actually back up a little bit. Do you guys need any help when it comes to the last homework question? Do you need me to post something on YouTube to help you with the implementation in MATLAB or Excel or whatever? Or do you want to do it by hand? If you want to do it by hand, that's all right. We don't need to have any of the discussion. But if you want me to post something, I probably won't be able to do anything during the weekend because I'm not in Colombia during the weekend, right? So I can't post anything. That's my problem. Yes. Otherwise, I would have posted something. So let me finish my thought. So if this is something you want me to do, then we can postpone the homework to like Tuesday or Wednesday, and like Wednesday morning. I will post the solution after the homework due date, right? Then I can post something on Monday for you to go over and help with the homework problem.
Personally, I would rather have the solutions, you know, to the other like 4 problems on Monday, and I'll take the hit on that like last problem I know how to do. That way I'll be better prepared.
That's okay. So let's do this then, because Fatima was asking for the same thing, and I assume most of you guys want to have the same thing, right? I'm going to remove the last question of the homework and add it to the next homework 4. Okay? Then you can submit your homework by Monday. We will do an exam review on Monday, and I will post like MATLAB implementation of this, or MATLAB or whatever, like Python, whatever, right? Of this, and then hopefully you should be good to go. Okay? Yeah. Okay. Okay. Yes.
When we finally do go get to that question for next homework, where we have to use the system, can't we, like, could we just use, they already create like code online where you just plug in your coefficients and you use like say A, B, C, D, and it'll just tell you what lambda 1 and 2.
For that system of unknowns and like equations, yeah, you can definitely use an already written code. But for the rest of it, for calculating A, B, and C, and D, I don't think there is anything online.
We were gonna solve that by hand, right?
You don't need to, but yeah, you can definitely solve that by hand. The programming part of it is pretty easy. I understand you don't have the confidence to do the programming by yourself, but when you see what I'm gonna post on YouTube, you will see that the programming, if you understand just this much MATLAB, like half a percent of MATLAB, you should be able to do it on your own. But I understand that you don't have the confidence to do it on your own. So you don't need to copy any code from anywhere. But if you want to, yeah, you're welcome to do so. That's all. I wouldn't care. Okay, so that's it for today. If you still have any questions about the exam and material, I'm going to stay here to answer questions. If not, see you on Monday. We are going to solve some example problems on Monday. If there is anything you want me to focus on Monday, send me an email, right? Because I'm going to focus on what I think is hard for you guys, right? Okay.